I'm Candice Lang. I'm Professor of Mechanical Engineering at Macquarie University. And what that means is that I'm the senior academic in mechanical engineering, and I oversee the mechanical engineering activity here, which is to say the research that gets done and the Bachelor of Engineering program that gets rolled out. So I want to talk to you a little bit today about becoming an engineer, how to become an engineer, what an engineer does. And what will become clear is that engineers do a million different things. So we really have to just touch on a couple of examples because we don't have time for more, but I hope the examples will give you some insight. So we should probably start out with being very clear on what is an engineer. And possibly all of you know already. But I have to tell you that I teach a lot of students who are already enrolled for engineering who don't know what an engineer is. So I'm going to start with what is an engineer. So this is my favorite definition. There are, like all things in engineering, a million different ones. An engineer is a person who designs and makes stuff. So that's the first thing about being an engineer. It's about designing and making stuff. If I were to list all the things that an engineer designs and makes, that would take the whole talk. So I'm not going to. I'll just give you some examples. An engineer is a person who designs and makes machines, bridges, vehicles, mobile phones, computers, radio networks. It just goes on forever. So I'd rather say an engineer is a person who designs and makes stuff. So if you like to design and make stuff, you should probably be an engineer. I like to design and make stuff. I'm an engineer, and it's good. So here's another example of a definition, and I'm just putting this up because it's from Engineers Australia, and that is the governing body for engineers in Australia, and they have a wonderful website. Their take is engineering is design. It's also making, but it's definitely design. And to differentiate it from science, research and analysis, that is science, but it's not engineering. And I think this is something that you need to have in your head, that both engineering and science are really important. But science only helps with understanding. Engineering helps with making stuff that aids the human race in whatever it is that they're doing. So practically everything in your possession is probably designed and made by engineers. Anything that isn't living and evolving is probably made and designed by engineers. So knowledge alone is of no consequence. This is from the website of Engineers Australia, to the future of life, if it does not manifest itself into some material significance through the design of whatever it is. I think that's a website you might want to take note of because it's really useful. There's a ton of useful stuff there. So that gives us some idea of what an engineer is in a generic sense. But what about particular types of engineers? There are many. So let's start off with, there are mechanical engineers like me. I'm a mechanical engineer. So obviously that's the best kind of engineer there is. So there are mechanical engineers, also electronic engineers. There are software engineers, civil engineers, and chemical engineers. Plus about 100 other kinds of engineers. But typically that is the group of engineering types that are offered at a university, and specialization could be at the bachelor's degree level, but it is more probably at postgraduate level. So to reduce this a little bit further, I should just tell you that at Macquarie University we offer mechanical, electronic, software, and a hybrid between electronic and mechanical, mechatronic. The others we leave for other universities, and I'll tell you a little bit about all of them now. So mechanical engineers design and build actually anything, but they design and build, for instance, vehicles of all kinds. And if any of you have been watching Sami Diasonos, you will know something about the work that we do on vehicles. Mechanical engineers design machinery of all kinds. They design manufacturing systems. They design heat flow systems. There's a ton of stuff that mechanical engineers do, but it's probably the most obvious type of engineering. We design and make stuff, physical things that you hold in your hand or use or are used to make the products that you use every day. That's mechanical engineering. Electronic engineers design and build the electronic circuits and systems that you use every single day in your phones, MP3 players, digital devices. We look at telecommunications, that's also allied to electronics. Anything that you do in the modern world that involves electronic circuits, that's electronic engineering. And then software engineering is much more than just coding. It is about designing and building whole programs, whole systems, so that what you want to happen will happen because it is being programmed correctly. So those are the big three that we focus on at Macquarie. But at other universities, you will also find civil engineering, which is mostly about designing and building infrastructure. Roads, bridges, buildings, things that we all rely on to make everyday life happen. Chemical engineering is the last one that I'll mention. It's mostly about designing and building processes for transforming, say, materials from one kind of material to another, or mixing things up to make something else. So anything that you use. Chemical engineers could have a lot to do with the process of making jam, for instance, or producing gold dust from some mining slag or whatever. So it's very much about process and process control. So those are the types of engineers that we have, and there are subtypes by the million. Let's just take an overview again. An engineer is a person who designs and makes things, and is therefore, first of all, you need to be a creative, out-the-box thinker. You really need to think about what is the alternate solution to this? Is it the obvious one? Engineers are resourceful. So if you're resourceful, engineering is good. It's about problem solving. Engineers are problem solvers. Just have a look at what the problem is, how can we solve it, how can we resolve it. And finally, engineers are hands-on. I'm going to talk more about this because being hands-on is really important to engineering. If you do engineering, you're going to get your hands dirty. That's the bottom line. It's not something that you can do far away from the action. It's a very hands-on career that you might make a choice for. I just want you to have a look at the photo that is with the text here, because I think that it covers a lot of the things that an engineer is. Those are three of my colleagues, and the task that they were given was, we've got this visit from some high school learners and get them making bottle rockets. I'm sure you've all made bottle rockets. You take a soft drink bottle, the plastic bottle, and fill it with water, pump it up, and see how far you can make it go. It's a very straightforward process. But my colleagues are engineers, and they thought, well, that's not really enough. Maybe what we should do is we should film it with our high-speed camera, 1,000 frames a second, so we can really see what's going on when the bottle rocket takes off. And furthermore, maybe we should make a backing board that's got stripes on it. You can see those, so that we can tell how fast it's going and at exactly what point things start to go a little crazy. And finally, why do we have just water coming out of the back? Maybe we should color it bright pink so that we can really see. So it's a simple problem here, but it's been taken apart by a group of engineers who've been saying, how can we do it slightly differently to make it slightly better? So this presentation, I understand, is for high school learners, and I would think that at high school, I hope that the most important question when you're thinking about a career is, will I get a job? Maybe you're not, and that's fine, but it certainly was quite important to me. So I would just suggest, in terms of engineering, just go and do a search, look at any careers website, look at any job or employment website, type in the word engineering. I did this the day before yesterday, and there are about 7,500 jobs for engineers out there. Australia doesn't have enough engineers. Australia needs more engineers. So if that's a career choice that you make, great. You are going into a region which has a lot of jobs available for a lot of new engineers, and that's good. So I want to talk about becoming an engineer. How do you become an engineer? What do you do to become an engineer? At the point at which you're looking at this right now, is it too late? Is it too early? Should you make the decision? Should you defer the decision? There's a lot of stuff which is going on in your head at the moment, and has been going on in the heads of people who are looking at engineering as a career. So becoming an engineer can be an incredibly straightforward thing. For those who can see the graph, along the horizontal axis is just your age in years, and on the vertical axis, just a nominal, what is your progression towards becoming an engineer? Assuming that you want to become an engineer and you will be done at some point when you have a degree. So when you're 0 to 5 years old, you're mostly making stuff. I think that most people make stuff when they're less than 5 years old. So that's good. That's an excellent start to becoming an engineer. Then you go to school, you work hard. This is the graph that everybody shows. Then age 10 to 15, you go to high school and you start studying maths and physics and chemistry at high school, and you study really hard. So starting to get a little bit outside my own reality, but I believe this is the case. And if you're doing this, great, don't stop. When you've finished your high school, you go to university and you study engineering, of course. What else would you study? And you do really well and you graduate with a degree in engineering, and then you're done. You're an engineer. So if you're doing this, please don't stop. It's wonderful. I think it's great. I just want to say two things about this. The first is that that word done at the top of the graph is not real. Engineers are never done. Engineers keep learning for life. In fact, it's in the Engineers Australia website. It is a requirement. It's a stage 1 competency that engineers must have, is the ability to learn for life. So when you've got your degree, you're in a position to have your first job, but you're not done. You won't be done forever. And that's the wonderful thing about engineering. You just have to keep learning. The second thing that I want to say about becoming an engineer is, although it may be straightforward, it might not. It might be very not straightforward. And I want to talk about that as well, because not everybody follows the perfect career path of going from making stuff before school to becoming an engineer in their late 20s. So looking at that again, we've got age in years on the horizontal, and we've got progress towards your career on the vertical. Let's have a look at what happens when someone is really just not done at the usual time. You make stuff for school, but perhaps when you're at school, if you don't really work hard enough, it happens. You don't study maths and science very hard. I thought maths was really cool at school. I thought science was the most boring thing on the planet, so I just didn't pay much attention to it. And then, of course, many people leave school and should study engineering, but they don't because they're doing something else. And then you might notice those blue dots are kind of starting to fall off now. They're not making a wonderful straight line because suddenly you're in your 20s and you're not done. And the reason that I wanted to show you this graph is not because it applies to you, I'm sure it doesn't, but it applied to me. That's my graph. I did all of those things, I did everything wrong, but luckily I recovered the situation later on in my 20s, started over, and I got it right second time round. So if anybody's in this place, I'd just like to say to you, the stuff that's past is past. You can do nothing about it, it's too late. But it's not too late to recover the situation, to do something different. So you can be an engineer by starting really early. You can also be an engineer by starting a bit late. It happens. So that's my graph. And what I wanted to tell you a little bit was how did I get here? What have I done? What is it like to be an engineer, to be me in engineering? And where does it take you? So, first of all, I started late at university. I hope none of you start late at university. It's a shame to waste time, but that's what I did, and it didn't matter too much. I didn't enroll for engineering. I enrolled for a Bachelor of Science, and I enrolled for a Bachelor of Science in Mathematics. Why? Because I thought mathematics was cool. It was not only cool, but it was also something that not everybody could do. So I thought, well, that's great. I really like it. And it's a little bit unusual, so presumably everybody will want to hire me because I'm good at maths. Then when I was busy studying mathematics, I discovered physics, which I had never discovered at high school. Never. But I suddenly realized that this was the most amazing stuff. I thought, gee, I've been wasting my life. I should be doing physics. So I kind of became a maths and physics geek. And then I thought, well, that's great. That's something not a lot of people can do, so I'll do it. And then reality hit. Where are the jobs? And society really needs mathematicians and physicists. There's no doubt about it. But man, it doesn't reward them. It really does not have a lot of jobs for maths and physicists. It really doesn't pay a lot of money to maths and physicists. I think it's a tragedy. But for me, it would have been a tragedy to take that career line because I really needed a job. So I switched. I graduated, and then I switched. I changed over to engineering. And that was absolutely the best decision I ever made. It was great. So I got involved in engineering, and I just kept going. I was having the best time. So I did my degree in engineering. I kept going all the way to a PhD, which is the highest degree you can get, because I was just having the best time. So in spite of the rather lurchy, rocky start to this process, I found where I wanted to be, and that was great. Since then, so for the last 20, 30 years, I suppose, I've been doing two things. I've been working at a university, and I've been working outside a university. So working outside a university is a little bit more engineering-y, and working inside a university is not viewed as by the public as very engineering-y, but they're both really important. And more important than that, I've just been having the time of my life. I've been having the best time. So whether I'm an engineer inside a university or outside a university, I'm having the best time. So I want to tell you a little bit about what I've done. And just to start with working outside the university, not going to be the same as any other engineer's experience, but it's an example of an engineering experience. So here's the story. About 10 or so years ago, a group of myself and fellow engineers started work to develop furnace technology for casting of metals. A furnace, if you're not familiar with one, it's essentially any kind of an oven, usually, that will go to reasonably high temperatures. If we're going to cast metals, we have to melt them. And if we're going to melt metals, generally that requires a pretty high temperature. So we were working on developing a furnace, particularly for the casting of metals, for the pouring of molten metal into a mold, and for that shape to be the ultimate shape that we want. It's not as simple as it might sound, because you need to get the metal really liquid, you need to get it flowing in a laminar sort of a way, and you need to get it freezing exactly as you want it to do. And this is what we developed. So as you can see, it's spectacularly ugly. It looks like a metal shoebox with coil sticking out the side. That was our furnace. I think it's pretty cool, but I understand that I'm biased. So it's an induction melting machine. And this induction melting machine had two amazing things. The first is it uses a single-phase power supply. Single-phase is domestic power supply. It's what you've got in your kitchen. It's what you've got in your bedroom at home. It's a wall socket that delivers not a lot of power. And we made an induction melter that uses just a wall socket. So that's pretty good. Most induction melters require three-phase, very heavy current. They are an absolute pain to use because you typically have an RF generator the size of a refrigerator and so on. So this little furnace was really great. Second amazing thing was that it could melt things. It could go to really high temperatures. So for instance, it melted platinum, 1800 degrees centigrade, in less than a minute. Which means, if you think about it, if you plug this into your kitchen next to the plugging in of the kettle, that they would draw about the same amount of power from the outlet, but this little baby would melt platinum faster than your kettle would boil water. So we thought that was amazingly cool and just not really something that anybody could say no to. Why would everybody not want something just like that? Of course, business requires different things, and the first thing we were told was that nobody is going to buy that. it just looks horrible. Just forget it. So I thought, okay, now we need it to look good. So as a nascent company, we took on board some folk that were in design, but design more for looks than for function, because the function was all there. It got all the function that we need, but we wanted to look like, what do we want it to look like? Well, something between a starship and a coffee machine would be good. So we wanted to look exceptionally cute and good to use, but very sort of sleek and very high tech. And that's what we got. It's exactly the same machine. It does exactly the same stuff. But it is apparently the kind of thing that people will buy, and people are not likely to buy our shoebox with a coil sitting next to it. So that was good. Now we developed this furnace. It incidentally would go to about 3,000 degrees if you wanted, and it still does its stuff in the same time and with the same power as a kettle. Not enough. Not enough. We needed to do something else. We needed to do some kind of a high-profile project which involved using our furnace to cast metal to deliver into a project to show what the technology could do so that people would believe it. So this is what we chose. This was being made at the time in the early 2000s. It's a mace, it's a parliamentary mace, but the most important thing about it is that it contains lots of pieces of metal castings. And the particular pieces that we were after were the difficult ones, because the difficult ones were what our furnace was exactly the answer to. So I have to tell you the story. I and my colleagues went to talk to someone who was overseeing this project, and we said, well, we believe you're having a problem. He said, yes, the platinum pieces are not so great, nobody can do them, and so on. And our business manager took over and persuaded that we were utterly able to do this, and signed the contract, and we literally had signed it by the time we walked out. It was completely terrifying. My eyes were like saucers when we got out onto the paper, and I said, Ali, are you crazy? Can we really do this? He said, no problem. So in a sense, we were committed. We had to do it, and we did it. So this is what we had to do. If you have a look at that picture of the mace, what you'll see is there are 3 items there. The top one, the long arrow, is a whole lot of little beads, tiny seed beads, which are stuck onto what we call a tree, but they'll be clipped off and polished and will become part of the beadwork. So platinum beads are one of the things we signed up to do. We also signed up to make 2 platinum rings, big rings, not wedding rings, that would underlie the various pieces that would go onto this particular mace. So to give you a sense of how that process went from there, we had to fulfill that contract, which had massive penalty clauses in it, and we had to finish it on time, and we had to, more than that, we had to produce pieces, components, that would reflect light appropriately. And I don't want to go into that except to say that that means you have to make sure that your finish is better than the wavelength of light, which is very tiny. It's about 1,000th of a millimeter. So here's a day in the life of trying really hard to get this contract out the door without incurring a penalty clause so that we can make this high-profile object that will make everybody buy the furnace. So the first thing you have to do is make the mold. If you're going to pour metal, you have to have some kind of a receptacle into which you pour the molten metal, and when the metal solidifies, which it does incredibly fast, then you have exactly the shape that the mold was. So the mold has to be the precise inverse of what it is that you want to make. So first thing, you have to make the molds. You'll see later on that the molds should not be permanent kind of molds. They should be disposable, and that means you make them from a kind of plaster of Paris. So you make the molds, and you make them according to exactly the sort of object that you want the molten material to solidify as. To get that right, you need to use the computer-aided designs, which are provided by the client that wants the object at the end of the day. So step number 1, make the molds. It's a long process. It involves mixing up a kind of a slurry from plaster of Paris, putting it into whatever the appropriate container is to hold the mold, and making exactly the right hole inside it, which you do by a lost wax process, which I won't go into now, so that you have a container which is just right for casting metal. Once you've made that mold, you have to heat it. That's a picture of my friend and colleague Camille, who's been heating a mold. And the reason that you heat a mold is because, if you think about it, the molten metal is at 1800 degrees. You pour it into a cold mold, the mold is just going to crack. You've got a tremendous thermal shock there. So the way that we could get around that, the way that anybody who's casting of this nature, doing casting of this nature does, is to make sure that the mold is really hot when the molten metal goes into it. So first of all, you have to heat the molds. You put them into a different furnace, not the one you're using for melting. And you heat them for several hours, get the temperature exactly right, so that you have exactly the right consistency of mold that your metal needs, and that you've got exactly the right temperature for pouring hot molten metal into. Then you transfer it to the induction melter, which is you've already seen, and that's what Camille's doing right now. She's taking a big pair of tongs, picking up the mold, trying not to drop it, and putting it into the induction caster. Next thing you do is heat the metal until it melts, and luckily that's really easy with our casting machine because it takes less than a minute. And it's more than just a nice thing, because of course if it took 6 hours to melt the metal, then by that time the mold would be cold. So this is an advantage for us. We melt the metal while the mold is still hot, and then you pour it into the mold. So that's good. So imagine there we're pouring quite a significant amount of platinum, a few hundred grams, so we're talking about a serious amount of money here. You don't want to drop it on the floor. You pour it into the molds, and it solidifies almost immediately. You allow the metal to cool in the mold because you really don't want to handle it when it's at 1000 degrees, so you just leave it there. You break the mold off. You'll recall that I did say that we use a mold which is disposable. This is the reason why we use a disposable mold. So break it off. And what should be left there is the absolute perfect platinum casting. It's exactly what the client wants. It's exactly what you've contracted to do. And you're now done and the job is over. Except that it never is, because you probably have got it wrong. And if the casting is not perfect, well, chuck the metal back into the melt and you start all over again. This process takes at least a day, probably 2, so it's not really a day in the life, it's a day and a bit in the life. Every time it doesn't look exactly the way that you have contracted for it to be, you start over and you do it again. We were absolutely crazy around this time because we had a limited amount of time. We'd promised to do the deal. We worked days, we worked nights. It was the best time. It was actually fun. We had a really, really good time. So let's just have a look at that project again. We had a high-profile project to show what the technology could do. The rings on the right-hand side there were about 0.5 kilo of platinum together. That's a lot of platinum. It's really expensive. It's about $1,000 an ounce at the moment. So that was an interesting project. And believe me, when we made sure that the finish was exactly as it should be and a little bit of dust fell on the floor, we kept the dust because it cost money. And of course the platinum beads. We needed 750. That was what we had to deliver. There are not 750 on that picture there. We had to do that many times and clip off the beads and remelt the rest in order to produce 750 perfect platinum beads. That's what we did. So that was an example of my working outside the university, doing interesting stuff, interesting engineering stuff. We spun out a company, and that was fun as well. Now I work inside a university, at Macquarie University, and that's a lot of fun too. So I'm going to tell you a little bit about that. This picture on the slide is just a pic of the library and some students sitting on the grass in front. I have to tell you, the library here is great. I've worked at many universities, but this really is a great library. And our engineering students, within the first few weeks of their engineering studies, which is when they come to university, first thing they do is learn how to use the library. We make sure they know, because it's an utter waste not to use a fabulous resource like this. Okay, so what do I do at Macquarie Uni? Well, I'm teaching the next generation of engineers, and that's a lot of fun. This picture here is not a particularly great picture, but I love it because that's day one of Introduction to Engineering, which is also about day one of year one. And one of the fabulous things that happens is we are generally overwhelmed by students. If this looks crowded, it is crowded. What we're doing there is we're opening other rooms so that we have got space to put engineers for their pracs, for their laboratories, for their tutorials. So that's the first thing. We have a lot of people coming in to do engineering and having a lot of fun. We need to teach them about what sort of engineering they might be doing, and as a result, they do a lot of different things. I'm not going to go into that now. But in mechanical engineering, which I have an understandable bias about, we do anything from the very big to the very small. There's an example of the very big. That's a wind tunnel. Wind tunnels are completely amazing, and our wind tunnel is amazing. It's so amazing we had to rebuild the room that it's in because it wasn't big enough for us to move in, but it's great. So we're into this very big stuff and also into very small stuff. The gentleman in the safety glasses is Gerard, and he's busy making jars and jars and jars of nanoparticles. Now, a nanoparticle is something which is about a nanometer in size, so it's a particle which is in size about 1/1,000,000th of 1 millimeter. It is a very, very tiny thing, and making them just right means that you can use them in engineering, but it's not easy. So we go from the very big all the way to the very small, and we try to understand what's going on and make stuff. That's really the critical thing. We need to make stuff because that's engineering. Understanding what's happening is chemistry and physics, and that's great. Making something as a result of that, that's engineering. I wanted to say something about getting your hands dirty, because engineering at Macquarie is very hands-on. It's extremely practical. All of the chemistry, physics, mathematics, computer science is still there. We haven't taken it out, but we have made sure that there's a lot of practical stuff. So there's a TAFE course, which our second year students do, in which they learn, for instance, to do some milling and some turning and some welding and so on, because we just don't believe that an engineer should go out there with an engineering degree unless they can do that stuff. Most unis do not do that stuff. We also have lots of practicals. So students get into the laboratory, they do a lot of hands-on work, they get their hands dirty, because we would like people to go out from here with a degree that allows them to use their hands to make stuff. It's about making stuff. And the right-hand two picks, or the left-hand pick over there, is from the TAFE course that is run for us, seeing there are students there that are learning to use lathes. The right-hand two picks are from the Human-Powered Racing project, and that's a bunch of people that, if you've watched Sammy, you will know, are trying to break the world land speed record for human-powered vehicles. So there's a team at Macquarie which is developing human-powered vehicles in order to give it a go and go to Nevada and break the world speed record, which is a fabulous example of engineering problem solving. Last up, I just want to give you a hint of what you might do if you decide to do engineering and you decide to do it at Macquarie. First of all, in year one, almost all engineers do pretty much the same stuff. So if you're enrolled from mechanical or electronic or software engineering, you'll do the same stuff. And what you'll see there is a list of the units that all our engineers do, sandwiched between Introduction to Engineering and a bunch of other units will be the science units: maths, physics, computer science. You have to have those. They're part of engineering. The engineering units are Intro to Engineering, which starts on day one. And then there's digital electronics. Whether or not you are an electronic engineer, you need digital electronics. There is a course on electrical and mechanical principles that everybody does, no matter what sort of engineer, because you need to understand that. If you have a look at how things are color-coded, the Introduction to Engineering, Digital Electronics, Electrical and Mechanical Properties are run by the engineering department for engineering students. The maths, physics, computer science are run by those respective departments, and they are done alongside science students. If you take a quick glance at your right, you'll see Wendy, who's busy with the Instron tensile testing machine, taking some notes there, and that's one of the many machines that will be used as part of our pracs. We're going to skip forward to year 4 because the year 2 and 3 depends on what sort of engineering you're doing. If you're doing mechanical engineering, you might be doing solid mechanics, fluid mechanics, heat and thermal, vibration, blah, blah. If you're doing electronics, you might be doing circuits and systems and so on. So second and third year, very focused. Final year, you will do advanced, whatever your kind of engineering is. And then you will do a bunch of units which are exactly the same for all engineers. Doesn't matter who you are. Systems design, engineering principles, and you need to do industry experience through your degree. Final top-up is your engineering major project. It's an individual project. Takes about 6 months. You're going to be making something according to whatever the requirements are, and that is required for every engineering student. Over on the right there, you see 2 of our students, Lily and someone else, who are having a look at a piece of equipment that they're going to be using. And I just wanted to say, as an almost final thing, that I particularly put these pictures up because they're all female engineering students. To some extent, people have said to me, oh, well, you're a woman, you should be talking about women in engineering. I'd say the following things. I don't really think about it too much for myself because I've been a woman in engineering for a long time. I do wish we had more women in engineering. We probably only have 10 or 15%. That's a bit sad. And ultimately, I would say it's such a great thing to do. I don't understand why more people don't do it. I don't understand why more women don't do it. But we're growing our cohort, and that's good. So finally, what I want to say is I'm having fun. If this is the sort of thing that would really give you some joy in your life, I think you should absolutely do it. You should start becoming an engineer. Thank you. The HR that you'll see in the HR guide is 80. It's not engraved because there are a number of pathways if your HR is a bit short of 80. But if you're at school, I would say aim for 80. And if for any reason you don't make it, well, we need to look at alternatives, because I think that what we have done is we've looked very carefully at HRs, and they're not necessarily a good predictor of how people will do, but they are the best predictor that we have. Absolutely working with students, no doubt about it. And perhaps that's not going to happen to everybody, but working with the first year students as they come out of school and they get an engineering project to do, and they don't do it that well, and then they get to do the second one and they just do it so much better. To see that growth in engineering discipline, engineering way of doing things, enjoyment of engineering, there's no doubt in my mind. That's the best part about my job. So the first job was overseas, a postdoctoral work overseas, and what that involved was essentially looking at it for advertisements, writing to people, trying to find a place to go. I think it's probably simpler if you try to get a job as an engineer with a Bachelor of Engineering, because as you'll know, if you go to the employment websites and simply look there for newly qualified engineer, I think it should be fairly straightforward. It is a profession which is sufficiently in demand that it's not something that you have to do a lot of wiggling for. I think I had to do a fair amount of effort because I'd finished a PhD and I wanted to take an academic path. For an engineer, I don't think it's a problem. I think that the critical things at high school are, it's the best time to really assimilate that maths, and secondary to that, the science. If you do maths as well as you can, it's central to everything in engineering, and it's kind of the difficult thing for someone like me who gives advice to people seeking a new career. I often have people coming to me late and sort of halfway through their career and say, I've been to TAFE, for instance, and I'm a really good hands-on engineer and I want to do university now. And what I have to say is, great, we'd love to have you, but just check that you can do the maths, because the maths is central. So I would say at high school, really work that maths, make sure that you understand it, because when you come to university, everything is different. You have to learn differently. It's an interesting experience as a lecturer to look at a sea of faces. I have about 360 in the first year class, and almost everybody in the room was the smartest kid in their class. So I've got 360 people who were all the smartest kid in their class. You have to behave and work differently at university. And if you've already got that maths under your belt, sorted out, and you can focus on what's happening, which is new at university, that's great. In terms of what you do at university, that's different. I would think that you need to really absorb how to go through the system and not do what I call gaming the system, just doing what's required because you're being strategic or you're overloaded or something like that. There really is a different way of addressing things at university, and I think that if you can take that on board early on, you should be fine. Yes, of course, absolutely. I would think that any motor car racing team that is looking to improve how it does is going to look at a number of things. Obviously, the best driver, the best car, and the best car is going to require the best airflow, and the best airflow is going to require a car that goes at high speeds. So we're going to, I mean, there's more mechanical engineering in there than you can imagine. So absolutely, I think that that's a given, that anything that involves vehicles needs mechanical engineers. So yes. In terms of studying, what it involves is, I would say there are three major groupings. There is your basic technical skills, so that's your maths, physics, computer science. You need to get that under your belt. Employers assume that you have that. I should actually tell you that when I started at Macquarie, I went and talked to people who employed engineers, and I said, what expertise would you value in a mechanical engineer who graduates from Macquarie? And nobody mentioned the technical skills, not because they didn't care about them, but because they assumed engineers would have them. So you need good maths, physics, computer science. Then there are your engineering technical skills. That will be most of your degree. So if it's mechanical engineering, you will do materials, you will do solid mechanics, you will do fluid mechanics, you'll do heat and thermodynamics, you will do a lot of design, computer-aided design and computer-aided manufacturing particularly, and you will take these to quite an advanced level, and then you will carry out a research project, which you will choose. It's an individual research project. There are a lot of choices that are put out there, but you're also welcome to put one together yourself, in which you will prove that you are able to do all the things that you've been learning. So it's a 4-year degree. It's a Bachelor of Engineering Honours. And we find that in that process, people change the way that they do things. They learn quite a lot in the process and come out as ready to start engineering. Not as fully made engineers, because you're not fully made ever, but ready to start. Then the job that you get, the sort of work that you do as a mechanical engineer, is incredibly varied. It's almost impossible to say what sort of work you will do. You will choose. So you might be involved in manufacturing, for instance. So you might be involved in setting up computer-aided manufacturing, which will require computer-aided design to start off with. You may be looking at issues like heat flow. You might be looking at new buildings and looking at what is the air conditioning requirements of a new high-rise in the center of town. You might be looking at a new type of false or prosthetic limb that allows people to gain some mobility again. You might be involved in something biomedical. It's almost impossible to say exactly what you'd be doing because the choices are very wide and there are a lot of jobs out there. I should just comment that Macquarie sits very nicely on a corridor, a light industrial corridor, where there are many medical firms with whom we are associated, and so biomedical type of work tends to be a fairly strong leaning for us. But mechanical engineering could be anything. Quick answer is yes, every engineering degree is 4 years. There are exceptions. The first and obvious exception is if you don't manage to get it done in 4 years, then it'll take you 4.5 or 5. But it's a 4-year degree. There are some universities that offer essentially a 5-year degree, 3 plus 2. You are not in a position to register as a professional engineer until you've completed the plus 2. So although at the end of that you have a slightly higher degree, I think you end up with a master's degree, that is the same entry point as the 4-year degree. So they're all a minimum of 4 years. Some of them are a little bit longer. Yes, no doubt about it. I think it's easier for many reasons. I think it's easier because people are less worried and prejudiced about it, which is great. I think it's also easier because, to some extent, women are sought after now because they often bring skills which have not been usual in engineering, or simply because there's some kind of a corporate policy. I think it's generally easier to be a woman in engineering now, and I'll just give you a very quick anecdote about that. When I became an engineer, to be an engineer, you actually had to be one of the boys. And if you were a woman, you had to be one of the boys as well. That was just how it was. And nowadays, it's not like that at all, and I'm just so pleased. It's great to see young women engineers who are doing well and standing out there and not really caring to be anyone except themselves. So, yeah. Thank you all for listening. It's great.